Today's material comes from chapter 21. Just hitting high points again, just like last time. First of all, let's imagine that there is a positive charge somewhere in space. Okay? And what if we had a small... Well, actually, let's change that. Let's make it a negative charge. We have a negative charge somewhere in space. And what if I had a small positive charge right here? What would tend to happen? Well, we know opposites attract, so we know there would be an attraction that way. What if it was a little bit farther away? Well, if it was a little farther away, well, remember that electric force is proportional to distance, so if the distance is higher, it's inversely proportional to distance, so the attraction would be greater. If we were even closer, the attraction would be smaller, and so forth. We have one over here, etc. So you see that if we have, and what this is often called, a test charge. If we had just some small positive charge and we could move it around and put it in different locations around this negative charge, we could gauge the relative strength of that negative charge, and we would see that, if we stay at a uniform distance away, we would have a bunch of locations like this that all have roughly the same force of attraction, and so forth. Alright, now if we changed this and all of a sudden we turned this instead now to a positive charge, what would happen? Well, all of these would stay the same magnitude, they'd just go the other direction, right? Because now we're trying to get away. Because identical charges repel. Okay. This notion is the notion of an electric field. That is, if we have a charge, it produces a field around it that governs the attraction or repulsion of either like or different charges that enter its area. It's this bizarre thing where, like I said, we were in space, so there's nothing conducting this force, it's just there. It's just this field of electric sort of energy, but energy is not quite the right word. It's just an electric field. Okay? I hope that was clear. Watch it over again if it wasn't. Raise your hand and get help if it wasn't. I'm not sure what else to tell you. Now, we can measure an electric field like this. E stands for electric field. The electric field is the force on a test charge Q prime, and we just talked about what a test charge was, divided by the charge. So if we know the force on a charge and the amount of the charge, we can find the electric field. And the electric field is a vector quantity, so it's going to have magnitude and direction. Alright. So let's do a real quick example. This is the one from your book on page 427. This is really simple. Okay, it says a positive test charge of 4.0 times 10 to the negative fifth. So we've got a test charge, that's Q prime, is our test charge, 4.0 times 10 to the negative fifth coulombs, is placed in an electric field. The force on it is 0.6 newtons. So the force on Q is 0.60 newtons at 10 degrees. And we want to know the magnitude and direction of the electric field. We want to know E. Well, like we just said, E is just F divided by Q. So that would be easy. We would do 0.6 divided by 4.0 times 10 to the negative fifth. So when we do that, we get 1.5 times 10 to the negative fourth. An electric field is measured in newtons per coulomb, which makes sense because we're doing force divided by charge. Force is newtons, charge is coulombs, newtons per coulomb. Alright, now, but we wanted the direction. Well, if it's a positive test charge, which we said it was, we see that it's a positive charge, it's really simple. The field is just in the direction of the force, and it's that simple. If it had been a different direction, it would still be the same. Like, they would still be the same direction. So as long as you have a positive test charge, like we have up here, finding the direction here is really easy. I'm sure some of you were afraid we were going to have to do like some trig with vectors and stuff, but we don't. It's really simple. Okay, so if you're asked to find an electric field, this is it. Simple stuff. Okay. Let's take a second and remember something that we did kind of a while back. Let's say that this is the surface of the Earth, and we have, actually, let's make this the surface of the Earth, and we've got some object above it. This object has potential energy. It has the ability to fall, right? If we had a different object up here, the potential energy is bigger, right? And if we had a different object down here, the potential energy would be smaller, right? Because potential energy is just the ability of the object to fall. This is gravitational potential energy. But I think that's clear to everyone. This can only fall that much. The purple one can fall that much. They can all fall different distances, so they have a different potential to fall. So in physics, there's something called electric potential. This is one of those things that I didn't understand very well the first couple times I learned about it. Electric potential. It's basically the same thing. If we have a positive charge and a negative charge, how much ability do these charges have to attract? Well, a certain amount. You know, they could attract this far, and we'll just do it one direction for simplicity. But what if my negative charge was way over here? Well, now they have the ability to attract that far. So here we have a smaller distance that we can travel. Here we have a greater distance that we can travel. Alright, what if we had two positive charges? Now these aren't going to attract, these are going to repel. Well, what potential do they have to repel? Well, they're relatively close. They have the ability to get quite far away from each other. They can go, you know, all the way over here. And we'll just do it with one again. But what if, and maybe there's a wall here at the edge of the screen. Maybe there's a wall. Okay, but what if I had one here instead? Well, he only has the potential to go to the wall. So this is kind of a weird thing. But when I talk about electric potential, I'm still just talking about the ability to change, the ability to either attract or repel. And in this case, let's assume that this one was fixed right here. So this would want to get over here, and so with this one. They both want to get away because similar signs repulse. I'll say the blue ones were both fixed. the red wants to go to the blue because opposite signs, opposite charges attract. So these have a lower potential. But the other pair has a higher potential, a higher ability to move. Here, these two have a higher potential because this can move all the way over here, but these two have a lower potential. Okay, electric potential is measured in volts, and a volt is a joule per coulomb. A volt is basically work per charge. And you've heard of volts before because that's, you know, what batteries are measured in and whatnot. A higher voltage just means, and these are volts, so this is higher voltage, this is lower voltage, this would be higher voltage, this would be lower voltage. Higher voltage means higher ability for the charges to move. Lower voltage means lower ability for the charges to move. That's what electric potential, which is voltage, means. And I didn't understand that for a long time, but if you just think of it as basically electric potential energy, just like gravitational potential energy, I think it makes a lot more sense. Okay. If we wanted to measure the voltage between 2 points in a field, so we've got point A and then point B over here, and there's some electrical field generated by some charge. We don't know what kind of charge, but there's an electrical field. How could we do it? Well, there's a very simple formula for voltage in an electrical field. V equals E D. That's the electrical field times the distance between the points. So I'm not even going to do an example of that because distance is just distance. That'll be given to you, and the electric field will be given to you. So that's simple enough. Just plug in. If you're asked about work, which you may be, work for electricity is defined as charge times voltage. So Q times V. And that's simple too. I'm not going to work examples of these two equations. Remember, voltage, this isn't the only definition of voltage. We'll do lots of things with voltage as we move forward. Not today, but eventually. But for today, voltage is, it's the potential to do work. Remember, the potential to move. It's the electric field times the distance between 2 points. This is voltage between 2 points. And the work done by moving a charge is the charge times the voltage. Okay. Last thing we need to talk about is capacitance and capacitors. Capacitance C, which is a variable C, is the ratio of charge to velocity. So if you're trying to do a problem, you're just going to use this formula, and it's very simple. By the way, V equals Q over C, and Q equals VC, because some of you, I swear, still can't do algebra, just by the way. But there's your formula, Q over V. What capacitance, or rather what a capacitor is a device that has a specific capacitance. And what's the utility of that? Well, the utility is a capacitor is used for a variety of things having to do with currents and circuits and etc. We can't really get into it right now, but you are going to be asked to find capacitance a little bit, and as you can see, it's really simple. The unit for capacitance is the farad. Not sure how to say that. It's a capital F is the unit for capacitance. It's named after Michael Faraday, who's sort of an important dude. So capacitance is measured in farads. So you should know that. And that's really all there is for today. You'll have problems just like normal. So enjoy.